So in this short video, we will look at pre-processing medical images prior to convolutional neural network analysis. If you open Notebook 3.2, you will see the concepts of this session's video demonstrated for a neuroimaging hippocampal dataset. Here, the hippocampus is a small structure in the brain, heavily involved in the processing of memory. It's therefore one of the first regions of the brain to show atrophy following a dementia diagnosis. So one thing we can do to reduce nuisance variability is perform spatial normalization to a global template space. This is because the convolutional operation is itself not scale invariant, and while networks may learn to be somewhat invariant to scale through pooling or downsampling operations, learning multi-scale features will just require more parameters and therefore increase the chances of overfitting. Hopefully you will have come across the concept of spatial normalization or image registration in your medical image computing or other similar courses. The idea is that we will learn a spatial transform of the data using combinations of rotations, translations, scales, and even deformable nonlinear transformations to bring all data into a common coordinate space where to a large extent it overlaps. The next thing we have to do is normalize the intensity range of the images. Intensity normalization is a standard pre-processing step for all CNN experiments, natural images included. This is because neural network training is sensitive to the absolute range of the samples, since the estimated gradients represent the rate of change of properties with respect to the original data and the current state of the parameters. Thus, without normalization, update step sizes would vary significantly across examples, which would disrupt or slow down the learning process. At the same time, normalization can help avoid population bias and improve generalization. For example, if feature ranges are different for train and test sets, this would mean that semantically similar train and test examples would generate different results without normalization. So the standard approaches for normalization are either to scale all images into the range 0 to 1 by dividing each through by its largest intensity value, or to normalize each one to have a mean of 0 and a standard deviation of 1. Histogram normalization approaches, on the other hand, are a more specialized approach, more common to medical imaging data and particularly non-quantitative imaging protocols such as MRI, where in the end, the best strategy for normalization will depend on whether the image is quantitative or not. So for quantitative images such as CT, it's probably fine to just take the standard approach of dividing through by the maximum. Whereas for non-quantitative and highly scanner-sensitive methods such as MRI, it may arguably be best to normalize by comparison to a population of other examples. So, as today in your tutorial and for your projects you will be using MRI, we're going to look in more detail at this histogram matching approach. So here, the high-level goal of histogram normalization is to non-linearly scale the intensity histograms of images to instead match some target histogram distribution. And while there are many documented approaches to do this, today we will look at the approach of Nile et al. From the year 2000, which seeks to deform histograms so as to match a mean histogram, which is estimated from a target population of images and has been transformed to a standard range. So the operation is performed through the following steps, which you will go through in the first exercise of the tutorial. So first, you need to estimate the intensity values that correspond to regularly spaced percentile intervals. For example, you want to estimate the intensity corresponding to the 10th, 20th, 30th, 40th, and so on percentiles up to 90 or 100. Here, by percentiles, we mean that we're looking for the intensity value that would result if you put all of the intensities in order and, if considering the 90th percentile, for example, selected the intensity for which 90% of values fell below it. This, for example, can be estimated from a cumulative distribution function. So once you have your percentiles for these landmark values, then you also need to estimate the intensities corresponding to the extremer percentiles. For example, you may choose your range to vary between the 5th and the 95th percentile of the distribution of your data, making the assumption that anything below the 5th and anything above the 95th probably represents noise. So once you've done that and you've got your intensity range of your current image, you then want to map that to some target or standard range, for example 0 to 100. You do this through interpolation. This intensity scaling then needs to be applied to the intensity of each of these landmarks. So you need to scale all of these percentiles, so the intensities you've got for all of these percentiles using this mapping that you've learnt at this stage. This is repeated for all of the images in the training or target population, where the intensity values of these rescaled landmarks are summed up and then averaged to return a target distribution or a target set of landmarks. Then, once you've got these target landmark intensities in this standard range, you go through your entire data set again, mapping the percentiles for the intensity ranges of each image into this target range. So the result looks a little bit like this, where here are the intensities of the percentiles of the input image and here are the target percentiles. And so you can see that this assumes that the relationship is piecewise linear, so scaling with a constant factor within each percentile bin. So finally then, there's the choice of whether to mask your image or not. So by masking, we mean removing and zeroing out any background structures. For example, when it comes to the human brain, it's common to mask out the skull. The advantage of doing this is that in principle, you then focus the network only on the tissue of interest, and in doing so, you reduce the memory and the amount of parameters required to be learnt. The problem is that the traditional image processing algorithms used to do this are not foolproof. They are also sensitive to intensity variations and noise. Sometimes they might go catastrophically wrong, sometimes they'll just leave part of the skull behind, which actually can be more of a problem, especially if the processing errors are biased towards some specific population in the dataset. Another issue is that CNNs really struggle with the sharp borders, spending far too many parameters in the model on this. Therefore, a compromise might be to mask, but make sure to smooth the image slightly at the borders of that masking operation. So, in summary, it may help for you to spatially normalize your images so as to remove nuisance variation and avoid wasting parameters on learning it. It's common, therefore, to use rigid or affine normalization, although nonlinear variation is actually more often addressed or modeled through data augmentation techniques. CNNs require normalized images. Typically, the approach is to divide through by the maximum intensity to return a range 0 to 1 or to standardize to mean 0 with a standard deviation of 1. However, for non-quantitative imaging protocols such as MRI, it may be better to instead perform histogram normalization, especially for data sets acquired across multiple scanners. And finally, giving a choice or masking or not masking, it may depend on the problem, but removing background will reduce image size and parameters to be learnt, so perhaps masking but smoothing at the borders is the best approach to take.